So we have been studying about ballistic transport in these lectures. We have found out that conductance and resistance is quantized if the channel length is of the order of its mean free path, and the cross-sectional area is of the order of the de Broglie wavelength of the electron, which is the Fermi wavelength in this case. So we found that in that particular kind of situation, the number of channels will be given by the width upon lambda f upon 2, which is the Fermi wavelength. As the width will increase in multiples of lambda f upon 2, there will be one channel added for every increase in W of the order of lambda f upon 2. If n will increase, so will the conductance, and it will also increase in quantum numbers. It will also increase in quantized ways. So it will always be a multiple of 2e square upon h. So the lowest value of conductance for the first channel will be 2e square upon h. So that number is called the conductance quantum. And similarly, the lowest resistance possible will be the resistance quantum. So it means that in a nanoscale, everything is almost quantized. The resistance is quantized, conductance is quantized, energy is quantized. And when we plot it, the conductance, it will look something like this. So for every increase in area, so area means nothing but the number of channels. So more the number of channels, more the cross-sectional area, and more the conductance. So initially the conductance is 2e square upon h, and as you increase area such that it is lambda f upon 2, multiple of lambda f upon 2, you have more conductance in steps. Okay, so now let's try to understand it from an example of a field effect transistor. So let's say that we're talking about a field effect transistor which has a source, drain, and a gate. So you know that in a transistor, if suppose that you apply a negative voltage at the gate, so because it is a metal here and then an insulator and then a semiconductor, so if it is a negative voltage here and if it is an n type material, the electrons will move away from this insulating layer. So here you'll have depletion region will increase, and therefore depletion region will increase, the channel width will decrease. So more the depletion region, lesser will be the channel width. So more the negative voltage applied, more the depletion region, lesser the channel width. So this is what we are understanding here as well. So here this is source, which is equivalent to the source here, drain is equivalent to this drain, and this channel here is actually equivalent to the channel that will be formed between the gate, between the source and the drain. And the length of this channel is assumed to be less than the mean free path, so that ballistic transport can take place. So this ballistic transport can take place when it is less than mean free path, but it is also dependent upon the number of channels that are there. So let's say that initially the gate voltage is 0, so it is larger radii of the channel is there, so ballistic transport is taking place. When the potential gets negative, this channel gets lower and narrower. So the number of channels that will be available here, they will decrease as the potential will become lesser and lesser. Okay. So initially, let us say if E maximum is the maximum energy permitted, then there will be n channels. So the maximum conductance will be given by the 2e square upon h up into n. So channel will narrow, as we see, as the potential will decrease, channel will narrow. But also at the same time, when the channel narrows down, the spacing between energy levels will be larger and larger. This is because of the quantization effect, which we have studied many times. That if the space in which the charge carriers are confined is decreased, the difference between energy levels will increase. So let's try to understand it better. So we see that if the spacing will increase, so lesser and lesser subbands will be occupied. Okay, so as n will decrease, narrower channels will be there, and G will also decrease. Conductance will decrease in integral units of G naught. G naught is nothing but 2e square upon h. Also, it depends drastically on temperature. So if temperature is larger, then the quantization will vanish. And why will it vanish? Let's try to understand it. So the amount of energy that will be provided to electrons by temperature will be kT. So if and at room temperature it will have a value of 0.025 electron volts. So let's try to see what is the energy difference between the two sub-levels, between the two sub-bands in a 10 nanometer square cross-section wire and in 1 nanometer square cross-section wire. In 10 nanometer square cross-section wire, delta E, it means the difference between energy levels will be 0.0113 electron volts, while if it is 1 nanometer square, it will be 1.13 electron volt square. So we see that this energy is lesser than the thermal energy that is provided by the temperature. So here quantization effect will be lost. Okay, while in this case it will be there. So you cannot get quantized conductance in such situation, while you will get quantized conduction in this situation, which is also depicted by the diagram here, where we see that as temperature is increasing, this graph will get flatter and flatter. So at a later state it will be something like this. So it will be like a bulk material. So but they say that okay, temperature, smaller temperature is important, lower cross section is important, also length is also very important, because if even at low temperatures the length is longer, then you cannot avoid any collisions. So collisions will be there, and if collisions are there, then G will not be quantized. Now we have been emphasizing that the electron moves drastically in this channel, in a quantum channel, and so if it is moving ballistically, then it means that resistance is zero. And if the resistance is zero in this channel, then how can we talk about a quantized resistance, quantized conductance, like we have said here that this will be the resistance. So what is how can we get this resistance? So this actual resistance is because of the contact resistance. So you see, we have discussed that there will be continuum of states in the reservoir, and when we are going from around infinite number of states to a fewer number of states, there will be a lot of traffic. That will be very difficult. The electrons will be very difficult to flow from here to here. So this contact resistance is actually, that is what gives rise to this resistance, okay, and dissipation of energy.